about 15-minute slots for each talk, maybe like roughly including questions. And yeah, so the first talk is by Michael from Berkeley, and it's going to continue the theme, I guess, of like Hamiltonian, like big states, Davis generator appears here, and yeah, take it away.
Yeah, absolutely. So I will be continuing on talking about Gibbs state preparation. And you've already heard a few talks about Gibbs state preparation. There's a whole bunch of new algorithms for preparing thermal states. And they work by simulating thermalization. Now, I'm kind of obsessed with food. So anytime somebody says system-bath interaction and thermal states, all I can think of is putting a steak in a sous vide. And this is really the first thing that comes to my mind. I have this steak that's being cooked over a long period of time. And the first question you should have when something is being thermalized over a long period of time is, when is dinner going to be ready? So ultimately, what we want to do with this project is we want to estimate the time to converge to equilibrium. This can be done in a variety of ways, depending on the norm you choose. Today, we're going to focus mostly on spectral gap estimates. So there's been a lot of progress that's been made. We've heard about some of this most recent progress this morning. And I wanted to just give you a broad overview of a couple of these places of progress. So we have things like classical non-interacting Hamiltonians with small perturbations. We have things like code Hamiltonian, so the Tor code being the chief example among them. High temperature lattice and mean field Hamiltonians, like we heard about this morning, and one-dimensional systems. Now, if you look at this list, it's some pretty marvelous accomplishments, but there is sort of a gaping hole, which is none of these have highly non-commuting interactions and a phase transition. And a lot of physically interesting models fall under this description. And what's really missing is we don't really have rigorous techniques to handle these sorts of systems. And so we thought, okay, can we come up with the easiest model which hits these criteria where we can actually say something about the spectral gap, like really sharply and rigorously? So we chose the Heisenberg interaction. So you take two qubits, take two spins, and what this interaction does intuitively is it says, if you guys are aligned, I'm going to reward you with lower energy. If you're anti-aligned, I'm going to punish you with higher energy. Now, if you try to do the Heisenberg interaction on with like local interactions, even that is quite hard. So we stepped back a little bit and we looked at what people in statistical mechanics do. They throw a mean field assumption at it. So what that means is I'm going to take these qubit-qubit interactions between I and j and replace them with an interaction between a qubit and the average of all of its neighbors. And this isn't unique to quantum in any way. Actually, people did this with the Curie-Weiss model. This is a mean field version of the Ising model. And it actually tells you a remarkable amount of information. It gives you things like upper bounds on the pressure. It gives you things like, oh, there is a critical temperature for sufficiently high dimensional models. And it even gives you upper bounds on those. Now, the model that we're going to consider here today is the mean field Heisenberg ferromagnet. And that is what it is. And the reason this model is so tractable is because it's extremely symmetric. So we have SU2 symmetry at each site. And one way I like to remember this is if I take a ferromagnet and I rotate it, it's still a ferromagnet. It also has permutation symmetry, and this comes from the mean field assumption. These two symmetries will be really driving pretty much any result that I talk about today. So just to convince you that I haven't just shown you a very boring model, it does exhibit a ferromagnetic-paramagnetic phase transition. So at high temperatures, there's no preferred direction. The spins are just kind of thrown out there in a mess. And in fact, one way to detect this is you just notice that the Gibbs state is actually invariant under all SU2 permutations in the infinite volume limit. At low temperatures, this sort of fractures, and these states will actually choose a preferred direction. And this actually is like sort of the physical basis for magnetism below the Curie point. The mechanism here is through SU2 symmetry breaking. That's what I mean when I say they choose a direction they prefer. So I haven't said anything about thermalization, and because it's a lightning talk, I won't say too much about thermalization. I will mostly outsource that to Tiago's talk from earlier. But our main model are these local Pauli models with the Davies generator. So I have single site Paulis acting on each site. They don't have a preferred direction. I just say take X, Y, and Z, add them all up, and construct the Davies generator, which has these scary omegas that tell you something operator Fourier transform E that's going on here. Like I said, I don't want to spend too much time on it. If you'd like to walk through it, I'm more than happy to after the talk. So let me just point out a couple key facts. So I have this Gibbs state. The dynamics are KMS detailed bounds, which really just boils down to a certain self-adjointness condition. So spectral theorem guarantees we have exclusively real eigenvalues. It's then not too hard to show that this particular generator is negative. So I mean that its eigenvalues are all not positive. You can then show it's ergodic, meaning this just fixes the Gibbs state. This corresponds to saying that its kernel is one-dimensional. And in particular, the spectral gap of this model is the first non-zero eigenvalue, which is negative. And intuitively, it's nice to think about this eigenvector corresponding to that as the slowest decaying mode. So what do we prove about this thing? What we want to characterize is how the rate of thermalization depends upon system size. So what we prove is the following. You fix a non-critical inverse temperature, so any beta, which is positive and not equal to 2. Then the spectral gap as a function of n satisfies that it's constant at high temperatures and 1 over n at low temperatures. And I want to emphasize that these are optimal, so these are both lower and upper bounds. This is the exact asymptotic scaling. I'm not hiding anything here. In particular, you'll notice that across beta equals 2, that was the location of the phase transition. This is exactly where we see the change in scaling. So these two are very interconnected. It says that the phase transition in the static picture has dynamic implications. So I'm in a rare situation to where, because the result is at least simple enough to get to this quickly, I can tell you a little bit about some of the proof techniques that we used. And ultimately, our hope is not just to stop at mean field models. We would like to eventually say something about more local, interesting models, and not just say, OK, maybe the others work similarly. And we hope that some of the proof techniques that we use might be extensible to these other models. This is unclear. I just want to at least share how we prove this. So the first observation is sort of a simple one and hardly unique to this approach. Physicists have been doing this for ages. This model has SU2 and SN symmetry, so it's permutation and SU2 symmetry. And sneakily, this local polynoise model, which is sort of a standard assumption, this also has this symmetry in the following sense. Acting by X, Y, and Z, that's sort of like a depolarizing channel on each site. I didn't ask for more of X, more of Y, more of Z. This has a hidden SU2 symmetry. Then I said that each site is the same. So I didn't pick any individual qubit to be more important than another. This also is permutation symmetry. What we prove, and it's really not hard to prove it once you have these two observations, is that the Davies generator inherits both of these symmetries. So long as your Hamiltonian has this and your noise model has this, your Davies generator will inherit it. This is not unique to the Davies generator. The same thing can be done for the CKG generator and other detailed balanced Lindbladians. So as a very simple consequence, we use Schur's lemma, the most powerful tool in any representation theorist toolbox. And it says that this is going to respect the decomposition. So I can split this up into permutation invariant observables and then other stuff. So one intuitive thing you might be thinking about this is if I am driving this system towards this Gibbs state, which I know is symmetric, I can imagine that as time goes on, this kind of looks like dissipation where I'm driving this other stuff to zero. So things slowly become more aligned or more symmetric. And intuitively, if you've read a lot about Markov chains, this might feel a little bit like diffusion on the permutation group. And this actually can be made precise in the following way. So we're going to introduce a new style of argument called the group mixer comparison argument. It consists of two steps, the first of which is the construction of something we call the group mixer. This is akin to some diffusion on SN. And the idea is pretty simple. You start with a Markov generator on a group. Here it's the permutation group, but it's bigger than that. And there's a beautiful paper by Bardet et al. Just a few years ago, which gives you this recipe for converting certain Markov generators on groups into Lindbladians on representations of that group. And what's more, this conversion process actually preserves a lot of salient properties of this Markov generator L. In particular, the spectral gap lower bounds the spectral gap of the Lindbladian. And so what that means is you go through this giant list of classical Markov chains, you find some that have a property that you really like, and then you can immediately import it to an interesting Lindbladian in the quantum setting. So you can find a chain that, in this case, has constant gap and its kernel is just a permutation variant. So this is what I mean by importing this diffusion process. Now, so far, I've just said there exists some other Lindbladian which does that. So I should really relate it back to the original problem and say something about the diffusion of the original model. That's done by a comparison argument. So what we show in particular is an operator inequality. We show that the Davies generator simulates this diffusion process, and this amounts to showing this inequality between these Dirichlet forms. In particular, even though this constant's a bit scary, it doesn't depend on n in any way, so it's completely independent of system size. Together, what's just happened is we've actually shown that this restriction to the other stuff is actually bounded away from 0 by uniform and n constant. Now, this isn't the end of the story. We still have all of these permutation invariant observables. For that, I'll let you read the paper, which hopefully will be out in just a couple of days. But I just wanted to give you some takeaways from this approach. This hopefully provides some new strategies and insights to leverage symmetry for bounding mixing times. So we have this group mixer comparison argument. There are other arguments that show up in this paper that, to our knowledge, are somewhat new. And we hope that they say something about analyzing systems with symmetry. And the hope is that we can use these ideas to handle models with phase transitions driven by spontaneous symmetry breaking. The golden standard, or the very long-term ambitious goal that I have no idea how close or far we are to handling, is the Heisenberg model with local interactions. The belief that is very closely related to some dangerously open mathematics conjectures that have been out for a while is that this mean field model should be a good prototype for local Heisenberg models in dimensions 3 and above. Now, actually characterizing how accurate these are, that's extremely delicate. But a lot of these questions actually haven't been asked on the thermalization side, and who knows, maybe these things are more amenable to these techniques. I'll take any questions. Thank you for your time.
Can you think that this dangerously close mathematical problem?
Yeah, so the dangerously close mathematical problem is that the Heisenberg ferromagnet in dimensions 3 and above exhibits symmetry breaking at low temperatures. This has been conjectured for, gosh, I don't even know when it started. They thought they proved it 50 years ago. Then they found an error in the proof, and they haven't fixed it since. And a lot of people have tried to attack this thing. And I can make that statement a little more precise if you would like, but that's the short version of it. And maybe for a bit more context, we know that in dimensions 1 and 2, they're sort of pathological in the sense that the Mermin-Wagner theorem prevents continuous symmetry breaking. In that case, dimension 3 is the first case where it's plausible, and a lot of physical calculations say, yeah, it should definitely happen here. Yeah?
Well, I don't know how to interpret this. Sometimes if I have a finite n, right? At low temperature, the Gibbs state is at zero temperature. It's something that has 50% mass on the all. Mm-hmm. Okay, maybe just thinking.
Is it 50 though?
It's not. Okay, what?
So in particular, it's a uniform distribution on SU2, which is continuous, and that's important.
I see. So it's saying that you have a slow mixing time to that uniform distribution.
Yes.
But
yes.
you could mix quickly something that looks like it's mostly aligned to something more fluctuation.
Absolutely, absolutely. So actually, one way to interpret this group mixer argument is essentially saying that on these things which are not permutation invariant, it does mix quickly. And the bottleneck exclusively comes from this SU2 symmetry breaking. And we actually, I didn't put this in the slides because I only had a few minutes, but you can actually show that the total magnetization order parameter witnesses the gap, in the sense that if you evaluate the Rayleigh quotient of the total magnetization, that thing completely matches the gap estimates we have for the Lindbladian. So sort of the same source of the phase transition in the static model also is the same source for the dynamic model. But one key difference between this and the Ising model, for instance, is that it's continuous symmetry. And so you have a lot more freedom to wiggle around there. You don't have to do this individual bit flip thing. You can continuously move. Yeah?
What do you mean by bottleneck? I guess it's an Ising model. I imagine there's two separate ones.
Yeah, so that's a great way to say it. So so the question was, what do I mean by bottleneck? And I suppose I just mean a slowdown. So I think for some people when they say bottleneck, that necessarily means an exponential slowdown. This is not an exponential. I guess I had somewhat naively believed that bottleneck meant any slowdown from fast mixing. And indeed, the mechanism physically seems to be from these Goldstone modes. And that's not unique to quantum. This happens classically too. I don't know which of you were first.
This is a clarifying question. So your results apply to the quantum or the classical Heisenberg?
Quantum.
Heisenberg.
Yes, yes.
And if they just rely on symmetry, it seems like they should work for both, right?
So the classical model has been well understood for a couple of years now. So you have to ask what your exact local noise model is. Probably the most appropriate reference is a result by Becker and Menegaki in 2021. They're called the ON models. And the dynamics they consider are called, I think it's Ginsburg-Landau dynamics. But they, in some sense, are the same. We actually didn't find out about this until partway through doing this, and then looked back and saw that actually they get the same scaling that we do, and it was like, oh, we should have known about that. But, things happen. Yeah.
The spectral gap that you obtained, does it extend to other detailed valence lambda?
That's a great question, and we really want to know about that. So if you see what Lindbladians that applies to, we'd be very happy to hear about it. But if your question is about other Lindbladians like CKG and that sort of thing, we know that the techniques that we have can get polynomial, sort of the same, close polynomial scaling. We're not totally confident about exactness, so sharpness in particular. So some of the arguments that we use incur extra factors of 1 over n. It's unclear whether those are fundamental or not.
Maybe we should move on to the next talk, but thanks again. It's dumb.
Perfect.
Great, yeah, thanks for having me. I'd like to share some new ideas on verifiable quantum advantage with you. So this is my pet problem for the last few years. Actually, I already gave a lightning talk about this 3 years ago. And back then I solicited a pizza challenge, whoever could break this obfuscation. I had to buy myself a pizza and a few more pizzas in the meantime. But last fall there was this amazing program here at Simons on tensor orbits, and I met Marcus and Yoming there, and I think we made some exciting progress. And I hope that there's a new challenge where hopefully I won't be having to buy pizza in the future. Okay, so what's the question? The question is to design a verifiable quantum advantage protocol which is really efficient and really compact, and I can put it on hopefully a quantum computer that's kind of near term in the sense that I'm targeting a regime where I have maybe 100 logical qubits and 1 million gates that I can do. So what's the setting? The setting is that I have a verifier who designs some challenge circuits, which he then sends to the prover, and the prover has to reply with samples from the output distribution of those circuits. Okay, so what are the desiderata on the circuits? Well, on the scheme, the idea should be that the correct samples actually require a quantum computer, and I can efficiently distinguish correct samples from fake samples using a classical computer. Does that make sense? Good. Okay, so people have thought about this a bit in the past, mostly in terms of what I call peaked circuits, or I guess what Scott has called peaked circuits, which I would define as follows. I would say that a family of peaked circuits is one which is, family of circuits which are classically hard to simulate, such that when I give you the circuit, recovering a key, so there's like a key to every circuit, recovering that key is classically intractable. But if I give you samples from the circuit, then there's some function I can apply to the samples, such that maybe the output of the function is 1 with probability that's non-negligible. Okay, so the paradigmatic example is, of course, there's one string which I see with larger than inverse polynomial probability. Does that make sense? Okay, I want to do something. Okay, and this is something that has originally been proposed by Shepard and Bremner in 2009, and they proposed a scheme which has since been broken. And Scott Aronson has brought this back on stage maybe a few years ago here at Simons in a few talks, and people have been starting to think about this more. But I don't think there's really a scheme, and it's kind of hard to come up with something here. So what we're doing now is something different. The idea is that we design circuits that have what I call a simulation secret. So what's that? It's a family of circuits, which is again classically hard, and has this additional property that they anti-concentrate. I'm not going to say exactly what that means. It sort of means that the distribution is actually flat, so it's not peaked. They're still keyed, so there's some secret encoded in the circuit. So now what I want is that, given the circuit, producing samples such that the XEB, so this is some statistical test on the samples, is larger than inverse polynomial, or maybe even constant, is classically intractable. And on the other hand, given the key, computing the amplitudes is classically easy in some sense. Okay, so classically, I would be able to evaluate the XEB because all I need to do that is to compute these amplitudes. Cool. Okay, so what's the approach? The approach is to use IQP circuits, but a slightly different family from the ones that Shepard and Bremner used, namely these cubic IQP circuits. So they're defined by a cubic Boolean polynomial. Okay, and the corresponding circuit has outcome probabilities which are exactly given by the gap of this polynomial. So the number of inputs that evaluate to 1 minus the number of inputs that evaluate to 0. Okay? This is a classically hard quantity. Okay, and indeed, simulating these circuits, if you just pick them randomly, is classically intractable. They also have this property of anti-concentration. And so that means if you just pick random IQP circuits, you can actually verify them inefficiently using XEB. Okay? Let me also say that an equivalent description of these circuits is just the coefficient tensor. So this is like a symmetric n by n by n tensor, which we'll think about as a cube of zeros and ones. Great. So the first observation, which was already there 3 years ago, is that there's an orbit of polynomials that I can construct given one cubic polynomial by just applying a linear map to the inputs. Okay, that just applies a linear map to the output as well. So it's something that I can efficiently undo classically. But if I, apply this to the input, I get an equivalent IQP circuit where, all the CCZ gates, so all the degree 3 terms, are extremely jumbled up. So maybe I started with something that was very easy. Maybe it had just 2 CCZ gates. Then I applied this affine transformation to the input. That's just a CNOT circuit. And now I get something that looks really random. That's the idea. Okay? But actually making something where you have some structure that you can exploit is kind of hard. So the idea is now to do the following. It's this idea of a planted independent subspace. So what's an independent subspace? It's a subspace of the Boolean hypercube, such that for every element of that subspace, the polynomial evaluates to 0. Okay? So why is it an independent subspace? Why do we call it an independent subspace? Because it's kind of a generalization of independent set. Okay. If we think about this in this Boolean, in this cube of coefficients, an independent subspace means that there's a basis such that there's a little 0 cube in some corner of this coefficient tensor. Okay? Good. So if we think about what it means to have an independent subspace in terms of the, I guess, hypergraph defined by this Boolean polynomial. So where I put a hyperedge on every term where I have a genuinely degree 3 term. Then having such an independent subspace of some dimension means that I have a vertex cover in some basis, namely this basis here, of the corresponding hypergraph. Okay? That means that I can express the gap of the polynomial as a sum over gaps of degree 2 polynomials, and that sum has just a number of terms, which is 2 to the complement of the vertex cover size. Okay? That was maybe a lot. Did that make sense? Okay, so if I have an independent subspace, that means there is a basis such that in that basis, the polynomial, or the hypergraph corresponding to the polynomial, has a non-trivial vertex cover. Okay? So a set of vertices that covers all the hyperedges. Yes? Okay, so if I have a large vertex cover, that means I can decompose the output amplitudes, or the gaps of the original polynomial, as a sum over gaps of certain degree 2 polynomials, where the sum ranges over the complement of the vertex cover. So if I have a really large vertex cover, that sum is really small. Okay? Okay, and I can efficiently compute the gaps of degree 2 polynomials. So this means that I have an algorithm for classically computing these amplitudes, which runs in time 2 to the n times 1 minus c if I've planted a c times n dimensional independent subspace. Yes? Okay. Whereas if I look at random IQP, the best algorithm we know for estimating amplitudes actually has runtime 2 to the n roughly. So now I have a polynomial gap between, the idea is now I give you the planted subspace as a secret. If I give you the secret, you can compute these amplitudes in time 2 to the n times 1 minus c. If you don't have the secret, you need time 2 to the n. So it's a polynomial speed up in computing these amplitudes if you know the subspace versus if you don't know the subspace. Okay. So now how do we get an advantage scheme from this? It's not an efficient verification, but if you buy the following two conjectures, it's a sort of polynomial gap between verification and simulation. And it would, for the first time, I guess if you ran this, really allow you to verify a circuit in a regime where you actually can't simulate it. Okay, so what are the conjectures? First conjecture is that, okay, let's look at this task. If I give you a cubic polynomial, decide if it's uniformly random or if it has a subspace, an h-dimensional independent subspace. Okay, the conjecture is that this actually requires genuinely exponential time if the dimension of the subspace is less than half of the full dimension. Okay, what's the picture? If I look at the dimension of the subspace from 0 to n all the way over here, then if I pick a random polynomial, it'll have a square root n-dimensional independent subspace. So this is sort of the information theoretic limit where you just can't distinguish, right? Up to dimension n over 2, the best algorithm we know has runtime 2 to the order n to the 1.5, which is basically just, finding a subspace which is maybe 2 times square root n dimensional. So you just sort of brute force find it. And then we found an algorithm if the dimension is larger than n over 2, which has runtime 2 to the n minus the dimension of the subspace times polynomial. So this is still kind of hard, but it would destroy our polynomial speedup. Yeah?
Do you think you could relate this to planted clique or one of these problems that have
Yeah, it's actually, so the way we think about it is as a lifted version of planted clique. Whereas in planted clique, I optimize, or I sort of look at the orbit of a, I guess, degree 2 polynomial, right, over permutations of the vertices. We're now looking at the orbit over the linear group, right, the general linear group. So it's like a much bigger group, which makes this problem much harder. And so the algorithms are actually kind of the same, right? So if you look at planted clique or planted independent set, the information theoretic limit is 2 times log n, and the sort of hard limit is square root n. And the best algorithm we have in between is 2 to the order log squared n, where the idea is, again, I just find an independent set of size maybe 3 times log n. Right? So this is exactly the same type of algorithm that we have here. And then there's a polytime algorithm if you have a larger than square root n independent set. So the idea is really that because we have this much larger group, it's really exponentially harder. Okay, I'm very confident in this conjecture. The next conjecture is a little bit more tentative, but I think it would be very surprising if it was false too. So that's now actually a conjecture if I give you a random. So the first conjecture was about distinguishing a planted instance from a random instance. Now we have to ask, so how hard is it to actually give you, if I give you a random IQP circuit to pass the XEB test? So the conjecture is that if I now give you a random cubic IQP circuit, producing strings that pass the XEB require time almost exponential, like almost linear, like genuinely linear in n. So why is there this little 2 to the 0.95 n? Because actually the best algorithm we know for estimating gaps of Boolean polynomials has runtime 2 to the 0.9961. It's kind of crazy that you can do better than 2 to the n. And the conjecture is that you can't do much better than this. And I think if you were to achieve, say, n over 2, that would really be a breakthrough, both in terms of just spoofing the XEB or computing outcome probabilities of IQP circuits. Good. Okay, so maybe there's one last question. Can you actually do something where you get efficient verification? Another observation as well, so what did we do? Basically what we did is we planted some structure such that the IQP circuit has a low-rank stabilizer decomposition. That was essentially the structure we planted. So now you could ask, oh, can I plant some other efficiently simulatable structure, say entanglement? So you could ask, oh, if I just had individual blocks which are unentangled, and then I obfuscate that, can you recover this? Turns out in this case you can actually recover it efficiently for any block size. You can do something maybe a little bit more sophisticated where you look at a low-depth IQP circuit on a line, which you could simulate with MPS. There the picture is not so clear, but it's kind of related to this min-rank problem, where you're sort of given a set of matrices and you're asked to find a linear combination of these matrices with low rank. So this can actually be solved in 2 to the order of the rank heuristically. So it's unclear how, if you can build something from entanglement. But maybe there are other structures where you could build something. With that, let me just very briefly summarize. So assuming my 2 exponential conjectures, there's a polynomial gap between verification and simulation for this task. What's nice about this, in contrast to peaked circuits, is that you can actually get an application. You can use this to get certifiable randomness using these ideas of Scott's and Sheehan's. Yeah, so the challenge, new challenge, are these conjectures true? Thanks. Yeah.
For the first conjecture, have you tried to relate it back to SET or something like that? Is it possible that it's related to one of these more standard?
Yeah. I've thought about it, but I haven't been able to. Yeah, would be interesting. Cool. Yeah.
Like a number 0.966.
Yeah.
Can you give some intuition for where that?
It's kind of a smart decomposition of the string into a small number of variables and a larger number of variables, and then you do some, I don't know, some efficient calculation to sort of compress it down. I don't have a very good intuition. So actually, this algorithm they somehow use matrix multiplication, and I think I had it here, right? So if you could do matrix multiplication in n squared time, you could even compress it down a little bit more. It's unclear I think if you wanted to go below that, you would really need a genuinely new idea. Yeah.
Thanks again.
One sec. Awesome. Okay. Hi, everyone. Yeah, I'm super excited to tell you about, my name is Rahul, and I'm super excited to tell you about some stuff I've been thinking about on a kind of unified way of computing with QLD-PC codes, which I've done with two really wonderful collaborators, Vedika and David. And maybe the best way to kind of motivate my talk is by just noting that in like the age of QLD-PC codes, we really understand how to efficiently and robustly store quantum information, but it's pretty unclear how to manipulate it. And in particular, if we have, say, a code with many logical qubits, we want to be able to treat these things as qubits and be able to individually address these things and entangle them in whatever way we want to. When there's a lot of kind of creative approaches in the literature for handling this, like code surgery protocols, code switching protocols, and kind of interesting criteria on transversal gates. But I think the general sense is that there's not really a systematic way to reason about computation on these codes. And just to kind of make this visceral, like before getting into a code with like 50 encoded logical qubits, let's just ask a very basic question, which is it possible to, let's say, do a CZ gate between the two logical qubits of a toric code, right, with unitaries, with constant depth unitaries? Somehow, it's not known. Currently, it was not known. You can ask, is it possible to do the Clifford group on the 2 qubits of the toric code, right? Also not known. And I think maybe my reaction to this problem was like, how do we even reason about this? How do you even think about this problem? And that's part of what we've been kind of working on. So in particular, the main message of my talk and our work is kind of that logical operations on some QLD-PC code C, like whichever one you would like. And when I say logical operations, I mean Clifford operations like transversal gates, code surgery, interblock, intra-block gates, or even magical operations like non-Clifford gates or more interesting forms of surgery like non-abelian surgery. All of these things can be seen as in correspondence with the Pauli logicals of some auxiliary code. And what I mean by that is every logical operation is labeled by some Pauli logical operator in some auxiliary code. And the kind of structure of this Pauli operator encodes the logical operation, like the way that you actually implement the logical operation on your code. So specifically, right, by deforming the Pauli logical in this kind of auxiliary code, we can deform the implementation. We can kind of change the way that we kind of do it on physical qubits. And as a result, this is kind of a tool for, maybe the initial implementation you get isn't like fault tolerant, but this is a tool for finding fault tolerant implementations of various logical operations. And these codes, these auxiliary codes aren't that complicated. They're just related to the hypergraph product, right, of the codes. If you start off with some code C, you take repeated hypergraph products of it, and you can use that to understand computation. So just to be concrete, if you want to understand the transversal gates in the 2D toric code, you study the Pauli logicals of the 4D toric code. Easy enough. And deforming these Pauli logicals tells you how to implement gates on the 2D toric code in a way that's fault tolerant. So, then, because we understand Pauli gates pretty well, like Pauli operators very well, especially in hypergraph product codes, right? We can just leverage our understanding of Paulis to compute like things like cleaning lemma and things like this. So specifically, we were able to use our approach, just to kind of have a little bit of advertisement, to show that you can do the full Clifford group on the 2 qubits of the toric code, right, with constant depth unitaries. Surprisingly, it was not known. So this includes new gates that we found, like you can do an S gate on either qubit. You can also do a CZ gate, between the 2 qubits of the toric code. In addition, right, in the 3D toric code, we found an exhaustive set of gates, subject to constraints from like Bravais-Koenig. So you can do a T gate on any qubit that you want to in a single toric code. You can also do a CCZ on, the 3 logical qubits of the 3D toric code, and a C0 between any 2. And in addition, we were able to find Clifford and non-Clifford gates on codes with many logical qubits. And not only is this kind of a convenient and very easy to think about way of reasoning about computation, it's also kind of a unifying perspective. Many different approaches that people have to computing, right, you can kind of organize and re-understand in this sort of framework. So in particular, I know for non-Clifford operations, there's a lot of rage on using the cup product to be able to cook up gates from these things, and you can show that we have as a technical term, a universal parametrization of all such cup products. So yeah, anyways, I think broad takeaway is that this is some unified, systematic, and useful framework for thinking about computation with QLDPC codes. So just to kind of give a flavor for how this works. So it's kind of well known, all right? If you work on QLDPC codes, or if you've heard of a QLDPC code, it's pretty well known that any CSS code you can kind of associate with a chain complex. What that means is that you have these vector spaces, and one of them is associated with the qubits or the Z operators of your code. Another of them is kind of associated with the stabilizers or kind of deformations of these Z operators, if you like, right? And this, kind of last level encodes how, a Z operator will violate the code space or create anions or something like this in whatever code you're dealing with. And then the homology classes of this chain complex correspond to the logical Pauli gates of that code, right? Either the X or Z gates of this code. And of course, these gates are deformable by stabilizers. And what we're going to show is kind of how do you encode logical operations like Clifford operations or non-Clifford operations all the way up the Clifford hierarchy in a similar chain complex language. How do you put not just Paulis on these things, but Cliffords and non-Clifford gates, organize them into a chain complex in some sense. And so, okay, it's useful to kind of review how people traditionally think about Clifford gates on these codes. So Cliffords are, of course, maps between Paulis, right? And so logical Clifford gates are represented as maps between chain complexes. So specifically, we have diagrams that look like this, which takes in one chain complex, which is shown in orange on the top, and spits out some chain complex on the bottom, which is shown in blue. And this diagram represents some map between X operators and Z operators, X stabilizers and Z stabilizers, and then similarly X syndromes and Z syndromes. And the fact that this diagram commutes is an indication that this operation is happening in a way that preserves the code space. So it's like a logical operation. And this thing specifically describes a logical CZ operation. And that's just because the CZ operator, done between 2 codes, let's say an orange and a blue code, right, maps X to Z, in some sense. And, these diagrams actually give you kind of physical implementations for how to do these gates, right? So you can encode, for example, the transversal CZ of 2 toric codes in this sort of way. And the key insight is that in the same way that we deform Pauli operators, right, with stabilizers, you can do the same thing but with Clifford operators. So you can deform, let's say, the CZ gates of a code in the same way that you would deform, right, the Pauli logical operators with Pauli stabilizers. And the way to see this is as follows. So let's say that we have 2 toric codes, and they have 2 copies of the toric code stabilizers, like X's and Z's in blue and orange. So this is what the Clifford stabilizers look like, right? Okay, and just to unpack this, what this gate is doing, each black line here is a CZ. And what it's doing is that it's taking a single qubit in orange here and mapping it to a plaquette in blue, right? So let's just think about what the action of this thing would be. So if I take in an X operator, right, on the orange code, and I act this CZ operator on this thing, it will map to, this plaquette Z operator here, right? In that sense, it takes any, X stabilizer to a product of X and Z stabilizers, and hence preserves the code space. Now this is a 5-qubit, or a 5-qubit gate, right? It's locally acting on the code, so it's completely logically trivial. So it's kind of equivalent in spirit to the Pauli logical operator, or Pauli stabilizers, sorry. These are local, they preserve the code space, and they're logically trivial. And just to kind of understand how we can understand this object, like in diagrams, right? In the same way that this thing mapped an edge in the orange qubit, in the orange toric code to a plaquette, right? We're going to map an X, In this diagram, down to the z checks kind of like this, like diagrammatically. It's going to be these diagonal maps is what encodes these objects. But crucially, this diagram doesn't need to be commute. Any diagonal map, right, I claim will create these kind of Clifford stabilizers. And the way to see that is that we can diagram chase. So you can kind of follow the diagram from C-1 over to C0, then back down to C1, right, by using this diagonal map to create a commutative diagram, right? That was kind of the thing that we saw earlier for logical gates, right? Yeah, so the high-level picture here is that we can convert these diagonal maps to things that point downwards by composing with the boundary maps of the QLDPC code. And this is reminiscent of the normal boundary map that we use, right? We can convert one type of object to another type of object by taking a boundary in a chain complex. We can do that similarly here. And actually, this intuition is precise. So in the same way that we organize the Z operators, the stabilizers, and the code space violations of Pauli operators in a chain complex, we can also do the same thing for Clifford operators. So we organize the Clifford operators into one level, right? Deformations of these Clifford operators into another level, and then code space violations into yet another level. And you can see that each level of the chain complex here now forms maps going downwards, maps going over by one, and maps coming towards me by one. And the logical operators corresponded to homology classes of the original chain complex. In this case, now logical Clifford operators correspond to homology classes of this new chain complex. And actually, we get something for free. It turns out code surgery is like one extra homology class, like present within here. So it's kind of a nice object in many ways. But OK, fine. I presented some like crazy chain complex. Like, how do I reason about this thing? Well, it's not so bad. A helpful analogy to make is vector spaces, right? So chains, and cochains are kind of like vectors, right? They form some vector space. And chain maps are kind of like matrices, but matrices also form a vector space. So, and it forms specifically the tensor product vector space. And so this chain map complex that I've been dealing with, this like complex of maps, seems complicated, but it's just related to the tensor product of the two codes that I'm mapping between, which is just a hypergraph product, right? If you're maybe more familiar with that. And so Clifford logical gates between C and D correspond to the Pauli logical operators in a precise sense, right, in the tensor product of D and C in some way. And you can use this to find gates. So how you do this is pick a logical Pauli operator in the higher dimensional code, right? And you can use that to specify what action it has on physical qubits, right? So for example, imagine that this side was the 4D toric code, then this is what it would this is the gate it would correspond to in the 2D toric code, right? And by kind of sparsifying, this logical, what I mean by deforming it in some way, right, we can come up with lower depth implementations of the gates that we want to do. And OK, I should note that you can also use this to extend beyond Cliffords, right? Because if we know that Paulis form a chain complex, and we know that maps between two Paulis themselves form a chain complex, which now looks like how we described Paulis, right? Then non-Clifford gates are just maps from Paulis to Cliffords, right? Like the next level of the Clifford hierarchy maps Paulis to Cliffords. Well, that maps Paulis to maps between Paulis. Well, we know that maps between Paulis now are kind of described by some higher dimensional code, right? And so we can re-understand maps between Paulis in this higher dimensional code as living kind of in the same way that we can describe this in the same way that we describe Cliffords. And then we can convert this now into some other code and then re-understand that in the way that we understand Pauli operators. Anyways, this formalism is super powerful, and we were able to do a bunch of fun stuff with it. I think it's actually just truly the surface of what you can kind of use when you learn to reason in this sort of way. Like, we found many new gates. We also found different types of gates that I didn't mention, like beyond CZs, you can do C0 gates, you can do S gates, T gates, intra-block gates, inter-block gates, whatever you'd like. And then in addition, you can kind of show that a lot of different other approaches to computation can be naturally kind of fit into this framework, which is nice. And then maybe coming soon, you can use this to actually just prove some very general results on, like, given a code, can you do a certain gate or can you not do a certain gate on it? And so hopefully that will be coming out within the next month. But the broad takeaway is that we've kind of come up with a nice, unified, systematic, and useful framework for thinking about computation with QLDPC codes. Yeah, thank you. Yeah. The full Clifford group?
Yeah, was wondering if there's a read.
Yeah, right. So that paper, I think you're talking about like the Gottesman paper. So, okay, transversal is like an overloaded term, I think. So I think they mean transversal as in depth 1. Our gates require at least depth 2. So, ours are constant depth implementations, unitary implementations of all of these gates. So depends on what your definition of transversal is, yeah. So I think their theorem is true for like depth 1, yeah.
Can you see well? Okay. Hi, good afternoon. I think it was a long day, so probably it's a good time to completely change the topic. And I'll be very happy to, just act for 10 minutes for some show. And this is about the string theory. And why do I talk about string theory? So from my viewpoint, there's something we can learn about some computational complexity, or more precisely, cryptographic hardness from another example in string theory, from what you've been hearing for the last several years, mostly from here or some other places. And this is about what I call string landscape. So let me just go through one by one what I mean by all this one. And this is not any finished work. This is something I'm going on steady and slow. And if you have any, you're all expert in a TCS and then approving whatever some random idea I just throw out. So if you have some good new thought from your direction, then please come and talk to me. I'll be very happy to share. Okay, so we have some hardware in string theory, something what I call the Calabi-Yau manifold. So maybe I'll just jump 2 steps further. So we have string theory in 10 dimensions. You've been probably hear that from newspaper. And we are living in 4 dimensions. So we have to do something about the extra 6 dimensions. So the extra 6 dimension, we have to compactify, so small size, whose size is so small that we cannot detect at our daily life, which we call low energy theory. So I have 4-dimensional space-time that where we live. And then on every space-time point, we have some manifold, which has roughly this kind of structure, that we have another one, and maybe something about here. So roughly I have 3 stacks, 3 stories of some Riemann surfaces, and they all together make 6-dimensional space. And this is basically what I mean is that this Riemann surface just fluctuate as you move around another second Riemann surface. And that together also, they move around in another Riemann surface. That makes a 6th dimension. So the number of genus and shape, all this one can vary a lot. And that basically makes the sort of the variety of these possible solutions. So okay, let's go back. So we have this Calabi-Yau, and not only that, on top of that, we have to do something to get the realistic world. And that realistic world requires turning on magnetic field inside each of those torus. Okay? And so that we call as hardware of the nature builds for 4 dimensions. And then low energy, in which we live in 4 dimensions, we are only observing certain small set of the data. And that we call as a text that's printed by the 10-dimensional string theory, and which hopefully the encodes all the informations of this 6-dimensional Calabi-Yau manifold. Okay, so then we as the physicist, our aim is that by doing a lot of experiment here, maybe some internal consistency checks, we want to understand what's hidden in behind, something we cannot see now, but from all this experimental data, I want to infer the 6-dimensional Calabi-Yau, what kind of manifold it is, and how they are organized, and what sort of magnetic field is turned on like that. So that's a decoding process. In plain English, I do experiment, and I want to understand God's mind in the 10 dimensions. And the claim we want to test is that this hardware could initiate some hardness primitives that we see in your guys' jargon, either in computational complexity or more in the cryptographic hardness. So for example, I will just go through some example later, but basically what we have is that we have this oldest secret n, which is huge dimensional vector, and then we have some linear transformation around around some certain particular point. Then this theta is the low energy observable we test in the experiment. And good enough, this theta is not the real valued continuous variable, but actually it's mod 1 circle valued quantity. And so how many these 6-dimensional Calabi-Yau can we have? And the physicists, they don't have any sort of guideline. They just do very simple one they can solve. All we need to do is solving this Einstein equation, which is a second-order elliptic partial differential equation, which is nonlinear, one of the hardest one in the computational scientific computing. And so that one we solved, and getting the geometry of it is completely formidable. I mean, there is no way we can do it. However, fortunately, for all this low energy experiment, we don't need actual shape. All we need is some particular subset of the data, but even that subset is formidable in the sense that we have to turn on huge flux inside here, and that the flux that we tested in some database we had is roughly this 10 to the 500. By the way, this 10 to the 500 has nothing to do with any scaling that you guys work with n. It's just some random number. The physicists just chose, oh, wow, that's the number that we got from some simple set of the rules that we compute, this geometry. That's called what is called the Tori Calabi-Yau, has something to do very similar to graph theory in your guys' jargon. Anyway, so this vector n, which is the discrete, the integer valued quantity, lives in the lattice space, which is associated with the cycles of the 6-dimensional manifold. For example, one real coordinate from each of the 3 tori, and then we make 3 dimensions, and we just count how many non-trivial cycles we have, and that's this flux lattice. And that number is typically very huge, typically order of 100 million, the 100,000 or a million. Yes.
Why don't I also have to choose a choice of the 6 manifold, and in addition to the integer fluxes?
Sorry, the trace?
Why don't you have to choose a pair of manifold in choice of the fluxes? Why just the fluxes?
No, okay, yeah, you're right. I mean, I just skipped that, okay. So we have the data of the bare Calabi-Yau manifold, and on top of that, we have magnetic field on it. So it's a combined one. Okay, but this complexity, which is 10 to the 500, what it makes is mostly coming from the magnetic field. Okay, so there are choices. And so by certain rules or the constraint of string theory, not every lattice choice, but each lattice is one of these huge, about 1 million component vector n, but that not every point is allowed. And there are certain quadratic relations, which is like this one, depending on the geometry and this vector. And I will mention that later, but there's certain constraints. So it's like some kind of the convex ball in this 1 million dimensional lattice space. And each of those choices, you just count them, and they make 10 to the 500. By no means 10 to the 500 is upper ceiling. It could be infinity. We have no idea as a string theorist. Okay, so here it is. So I'm just redrawing here, so I will be very quick. So we are doing in the 4 dimension here, and then at every point we have this Calabi-Yau. And inside Calabi-Yau, we have this old electromagnetic field. My drawing is bad, poor. And that low energy people like us, we describe certain the oldest experiment in certain rules, and that is called effective field theory. If you are just just complete blank, you might think of this effective field theory in your jargon as like transverse field Ising model, okay? And then where is it coming from? As a string theorist, I would say, okay, yeah, you string theory. You compute it. And you just, day and night, you just crank up your grad student. And one day he will come back and say, oh, yeah, I have a transverse field Ising model. Good. Well, then that's the leading term. Much like your Hamiltonian learning, you may say, okay, what's the next term? I just try to give a hard time to him or her. Okay, go back and compute the next term. Then he will or she will find full spin term in local term. Okay, good. Next one. So I just give him or her, try to find the complete list of the local terms in Hamiltonian, and he will or she will go forever, he never graduate, right? Okay. So that's basically what we are doing. Okay. So we just compute local terms in some Hamiltonian or Lagrangian. That's what we call effective field theory. They are organized in terms of the what we call dimension, or in your case, K design, how many local terms you have like that. And these are all eventually the solutions of this Einstein equation, as I said. And the flux is, as I said, about 10 to the 500. That's the kind of benchmark number. Now, you may already, several years ago, you've been hearing all this very nice, the intersection with the high energy physics, or maybe in string theory. One instance is this Hayden-Harlow, the black hole decoding. So you have a black hole. What is a black hole? To you guys, it's basically solving Einstein equation, okay, at a static time-independent solution. So you just solve this one, and you find that there's singularity, and to shield that singularity, somehow nature works in such a way there's a horizon, and once you have your horizon, then there's detachment of the causality between inside and outside. And then there's a Hawking radiation coming out due to quantum effect of the matter or the graviton fluctuation in that background. And then there was an outstanding puzzle of the last half century by Hawking that there's an information loss in this process. I don't want to go into detail, but the Hayden and Harlow came out and say, we have a way of understanding that in a computational complexity that decoding your Hawking radiation is going to be completely impossible within the Pauli time. Okay, sounds great. However, there's one thorny assumption that when you do this computation, when you go back to the Hayden-Harlow, they made a certain tacit assumption about your transverse field Ising model. They assumed the Hilbert space factorized, and they assumed that everything is the regular when you approach the horizon. Those two are completely invalid if you really work hard. And because it's gravity has some sort of what is called dynamical gauge symmetry. And as you approach the horizon, then there's a super Planckian boost to the high energy. So the effective field theory breaks down. That means the question, the framework of your question breaks down. So even though this question was very nice, and you can just isolate it as just oracle, and okay, I'm happy, I don't care about nature, black hole, whatever hole, and there's that problem, that's completely fine. But when you try to relate to the nature, then there's this thorny problem. Basically, it has the breakdown of the effective field theory. Okay. Now, next one, holography. I mean, the Umesh has been pioneering on this one. You have similar one, in this case, a dictionary. Now, there's some sort of the identity between the what is called ADL, anti-de Sitter-space boundary field theory, and the bulk gravity. And again, this bulk gravity solution of Einstein equation, nothing more different from black hole. In that case, what Umesh was asking was the following question. I just wait long enough of the boundary theory at finite temperature. And then that's the eternal black hole. And then in that black hole, I just ask some questions, super microscopic fluctuations in there, and then ask whether you can decode it, okay? And basically, that dictionary breaks down because it's exponentially hard. However, this one again is again, as a TCS problem, is very nice. However, it's kind of going orthogonal from physics because we are asking some post-thermal, contrived process in the thermalized system. So everything is already very quiet and macroscopically. And furthermore, when you turn on to the weak string coupling, then black hole disappears, and there's only strings which is like a floppy and whose size is as large as the macroscopic 4-dimensional universe, something completely different. But nevertheless, their argument has nothing to do with the coupling constant. So therefore, again, there's some sort of the exponential hardness, which is unbelievable because that theory we know how to deal with. So again, this effective field theory breaks down. So compared to that, I want to solve it. I just made some boxed one here, all in cases. Here we are solving Einstein equation. So all different solutions, okay? And in this case, vacuum counting is far superior, in my view, compared to black hole or ADS holography. The reason is because here you have like a horizon, observers, and entanglement, and the dynamics, and all quantum hardwares, which one is maximally entangled and so on. And that's very complicated. And I don't think that's the core of the problem or core of the feature. And what I just advocate is that if you look at the vacuum counting, which is basically what solves Einstein equation, how many solutions you have, and what is sort of the complexity of that, that semi-classical hardware, even though, the benchmark 10 to the 500, we have no horizon, no observer issue, everything's very semi-classical. So, and therefore, effective field theory, which is the sort of Bible that we write down how to do proceed your computation at low energy and then to try to decode, that's actually very well defined. And there's no issue whatsoever. Okay? So this is just ordinary complexity class as much as you can get from physics. So here it is. What are the observables we have? I just want to give you a very simple example. We have the neutron, proton, and that theory is called QCD. And for some reason we don't understand, there's a vacuum angle which takes a value from 0 to 2 pi on a circle. And that angle theta bar is extremely small, up to experimental accuracy 10 to the minus 10. Okay, this is a very small number. However, it's not a small number for our purpose. However, it turned out to be that when I do the string theory, there's an analog of this kind of angular one, as many as like 10 to the 6. In other words, there are circular modular variable in low energy effective theory in transverse field Ising model, much like Heisenberg with the analog Heisenberg XY model type. We have a 10 to the 6, 1 million circular variable in my low energy theory. Okay? And we want to measure their value, like a ferromagnetic phase, in which direction it direct on. And so we have some value on a circle. Okay? And once we measure those value theta, then we want to go back to the Calabi-Yau, and we want to pin down at which point out of 10 to the 500 we are sitting at. Okay? As I said, this from this flux data and on Calabi-Yau to the theta value, this is very trivial. I just pick one value in number and plug in, and in polynomial time, you just get the solution. But the reverse direction is not so clear. So writing is easy, and the reading is very hard. So basically, there are several situations. So a forward direction, as I said, is just very deterministic. How many times?
Oh, I think maybe like 1 more minute.
Oh, okay, sure. Okay. Yeah, so I'll just probably skip. And so anyway, this is very easy. And we want to focus on the decoding. So I start with IR and try to go up in the UV. And on this way of we going up, we just try to find out whether we are on the right vacuum or not. And then on the way, we may have several broken ladder steps. And we want to figure out whether those we are really kind of fatal, or we can just get over all this one and get the complete informations. And Bratkowski several years ago made a very nice the summary of all this one. Even though he used the Hadron-Harlow black hole, the framing is actually very precise and interesting. And he basically said that we should consider, in all this cryptographic context, we should consider EFI pair that's efficiently sampleable, but statistically very far, but computationally very indistinguishable pairs. And we have to test that once we have it with this black hole or Calabi-Yau or whatever, transverse field Ising model, whatever, then you have a good candidate for the quantum cryptography. So there are several layers, search and counting, and it's basically you need test this EFI. And so basically we have this now the new sort of problem as I advocate, which is counting the vector, which is the decoding starting from the data. So this is about the counting, nothing about the dynamics, okay? And basically this one is the goal we are after. And there's some provable hardness. Yeah, so in this case, basically the many cases, you might be just happy with the worst case. For physics, this is totally useless. I mean, that's the worst case, and physics always do approximation. We can get away. The typical case is more interesting. So in this case, this problem that I alluded basically corresponds to the short integer solution or the inhomogeneous version of it. And these are all, as you know very well, is tools in post-quantum cryptography. And that problem arises exactly in this context. And also there, on top of that, we have security parameters offered by string theory. It's not just the one, we have many. I don't know which one is better one, but at least we have how many fluxes we have, starting from that all the way down to control, leak, all kind of control, we have that. So basically I tried several things. My power is very weak. And so I tried, and then I basically first categorized that we needed 3 of them, some the conditions, which I borrowed from the cryptography. And every example I worked on, it only satisfies 2, not the 3. So it's in a sense, some failure.
Sorry to interrupt you. I think we should.
Yeah. Okay. Good.
Is this your last slide? Or?
Okay. Yeah. So basically, so here I have nature basically handed us something interesting, kind of one-ish object, which is totally static and this counting problem. And the sharp open problem is that this period structured, this lattice problem, does it have any the cryptographic hardness? And here, if you can forget about everything, why physicists are interested in this one. If there is any instance we find which is information theoretically complete, and at the same time cryptographically very hard, exponentially hard, what it means is that the dogma we are using in theoretical physics is completely shattered out, meaning that the effective field theory, ideology, this all breaks down. So we have to really go back and then just start from the rules again. So this is a one-way directional, and I think this one is very interesting and very clean and clear than black hole or ADS-CFT because it doesn't involve any dynamics. So if there's anyone interested in this problem, please just approach me, and I'll be very happy to share all my thoughts. Thank you.
Maybe we should save questions for later, just so that there's some time. So also, so we have 3 speakers left and space for 1. So one question I would like to ask the audience is, how do people feel about doing 2 of the speakers during the open discussion section on Wednesday? Will you raise your hand if you would be willing and able to come to that? Okay, let's do that because I don't want to tire everyone out. So I think out of them, you have a time constraint. Joe, are you okay doing Wednesday? Are you okay doing Wednesday also? Okay, great. So maybe we can have you as the last for today, and then we'll do the last 2 on Wednesday. I guess our last slide is by Greg Gluck, who is, wait, are you officially at Berkeley or MIT?
Berkeley.
Berkeley. It was at Berkeley.
2 floors above.
2 floors above. With Shafi, I guess.
Yeah.
Telling us about crypto and non-locale.
So that's, I didn't plan that, but it's kind of related to the previous talk, in some sense, at least maybe morally. So, okay. So the title is, universal computational non-locality and quantum crypto. So yeah, that's a paper that's gonna be out soon, hopefully. So just to remind everyone, I guess everyone knows the CHSH game, but just to remind everyone the setup, right? We have Alice and Bob that share an EPR pair or just randomness, and then there exists a game such that with the EPR pair, they can win with higher probability than compared to just having classical randomness. So that's very standard. So what is really happening in that game is essentially showing that there exists entangled state, which is the EPR pair, such that the corresponding game is non-local. So let's give maybe slightly more formal definition of what does it mean. What does entanglement mean? What does non-locality mean? So entanglement, again, that's everyone knows. A state is separable when it's a product state, like a mixture of product states. Otherwise, it's entangled. And we say that the state is non-local if there exists a game like before, such that when Alice and Bob have access to state raw, they can win with higher probability than compared to having only public shared randomness. Great. So these are the two definitions, and now one can ask, okay, are the two notions equal? Okay, the title of the slide says no, but maybe slightly more slowly. Let's see, every separable state is local. That should be quite clear exactly from that decomposition, right? Because whatever Alice and Bob can do with that state here, they can do with public randomness when essentially the index I in this is distributed through the hidden variable, and then they can reconstruct the state sigma A, sigma B, and do whatever they were supposed to do. Good, but the other direction is not clear, and what turns out, what turns out is that there exists entangled states that are local. And some of them are the so-called Werner states, which are super simple. These are just, that's just an EPR pair plus some amount of noise. And I'm not a physicist originally, not at all, but from what I understand, that was somehow or somewhat surprising to physicists, and physicists somehow don't like it, because ideally there should be an operational equivalence between entanglement, there should be an equivalence between entanglement and some operational notion, like, let's say, a game like that. But it turns out it's not the case. So that's why they don't like it, and there was a lot of studies around this question. So maybe one summary of what people know is people look at these Werner states with different values of p, and let's say the first game that I showed, the CHSH game, it works for p up to from 1 to 1 over square root of 2. There are some better games known, but for us, importantly, the interesting regime is the one in red, where for these states are entangled. So every state above 1/3 is entangled, but nevertheless, it is local.
What is the state phi?
Phi? Phi is the EPR pair. Yeah. Okay, any other questions? Okay. Good. So that's what is known in the information theoretic case for the Bell scenario games. And then in a paper with Andrew and a few years back, we consider a scenario where now everyone in the game is computationally bounded. So everyone is BQP, Alice, Bob, and let's think that the verifier is polynomial time classical. And we define locality and non-locality essentially in the same way as before, just putting computational restrictions on all the parties. And we show two things in that other paper. One is that assuming quantum hardness of LWE, we show that now every entangled state is computationally non-local. So now the notion of entanglement and non-locality, computational non-locality coincide, are equal. And then we also show like the other direction or a lower bound. We show that if every entangled state is computationally non-local, then BQP is not equal to PP. Okay, which is some separation of complexity classes. Maybe it's not super important exactly what it is, but it's interesting that there is some non-trivial separation. Good. So that's what was known before. And now, okay, now we give a name to that assumption that every entangled state is computationally non-local. Okay, we call it that, UCN. And that's the summary of what was shown before, right? Quantum LWE implies UCN, and UCN implies BQP is not equal to PP. There were similar arrows in the previous talk, so that's good. Okay. So the question is, does UCN imply quantum cryptography? So does it imply something stronger than just worst case separation of complexity classes, and even more, is it useful cryptography? So, okay, so that's the question we pose, and we answer positively. So we show three results. The first one is that UCN implies one-way puzzles, so probably most people know what they are, but I will explain shortly. And two more results. Maybe let's first look at the third one. So we show that, okay, a version of UCN with independent questions, I will say in a second what it is, implies something called oblivious state preparation. That's a cryptographic notion that was considered before. And what I mean by independent questions is that compared to the previous picture that we had, where the questions X and Y could be correlated to Alice and Bob, here I consider a case where they are independent. Okay, which one can claim is a natural assumption from the physical point of view, because if the questions are correlated, then it's not super clear how one would distribute them to distant places without violating the locality loophole. But from like more TCS perspective, it's not super clear a priori which of the two models makes more sense. Okay, so maybe let's go forward. Okay, maybe let's jump through that. Okay, so what is a one-way puzzle? So it's kind of like a one-way function for quantum, one can say. So what it is one algorithm that samples a puzzle and an answer, and there is some predicate that decides if an answer is a correct, if a given answer is a correct answer for a puzzle, but that predicate might be inefficient, and the main security guarantee given by the one-way puzzle is that when one gets only a puzzle, it's hard to find a solution. Okay? Great. So that's it. And now let's see how can we show that UCN implies one-way puzzles. So essentially what we do, we need to look at states in that interesting regime where they are entangled, but information theoretically local, and somehow use the fact that by the assumption they are computationally non-local, but information theoretically local, to arrive at a proof that the cryptographic primitive does indeed exist. So we look at essentially physics literature for different simulations with different structural properties that allow us to do it. So one such simulation is where it's a simulation for some state. It's not super important what it is. It's an entangled state and the simulation has two properties. One is that the local hidden variable comes from a constant sized set. And the second property is that the simulation on the Bob side is equal to Bob's original honest algorithm. Okay, so we take that we take that and we build a one-way puzzle. How do we do that? So we essentially will show that that state is entangled, so there exists a game that certifies its computational non-locality, and we will show that the pair of questions x and y generated by the verifier is a one-way puzzle. Okay, why is it so? So the important observation is that, okay, if we take, good, so let A, B be honest strategies that certify computational non-locality, and by the fact that there exists local simulation with lambda, the local hidden variable coming from a constant sized set, is that we can write this equation here, which essentially means that the thing on the left is the honest Alice's strategy, and the thing on the right is a mixture of m different distributions. And a distribution, let's say when Alice gets x and a lambda, she would like to sample from a distribution A infinity x lambda, but that might be an inefficient procedure. So instead of doing that, what she can do, she can sample from the honest strategy A run on state. Okay, maybe let me. So let's see. Maybe let me try again. Good. So maybe let's look at points 1, 2, 3. Points 1, 2, 3 define an algorithm that I claim is also a local simulation for Alice. And what the algorithm does is something very simple. The Alice essentially samples A from the marginal of the distribution of the correct answers given x, and then she wants to estimate the acceptance probability of the verifier if she returned that A. So that's point number 2. But to estimate the success probability of the verifier, she importantly needs to be able to sample y given x, which is the question for Bob given her own question. And that's and if one-way puzzles don't exist, such a computation is efficient. And if she then repeats that process many times and returns the result with a high acceptance probability, then that will be a good answer. So probably there's like a lot of moving pieces. So maybe it's not on the first sight obvious how they all fit together, but that's essentially the whole proof of the result of this part. So okay, so maybe let's skip this one And okay, let me go quickly through the maybe the more involved result, where we show that a slightly restricted version of the UCN conjecture implies now something stronger than one-way puzzle, which is something called oblivious state preparation. So what that is, it's a protocol between a sender and a receiver, where the sender can prepare only with classical communication can prepare a quantum state on the receiver's side, such that the receiver knows less about the state than the sender. So that's why it's called oblivious state preparation. I prepare a state in the other guy's head, and I know more about that state than the other guy. And okay, here's a formal definition, but we don't need to look at it closely. The only thing maybe that's important is that it's a different notion that considered before in the literature. So the OSP primitive was considered before, but our notion is different and at least we think incomparable. And okay, just to say one thing. So our notion of how well does a party know a state is essentially these two things, which mean how well can I find a classical description of a state that's close by in the trace norm to the one that was really prepared. Okay? Some notion. Great. So now, maybe I'm not going to bore you with all the details, but again, what happens for this proof is now we find a different local simulation result from the literature with different structural properties that this time allows us to show another primitive. And maybe we only want to look at these points 1, 2, 3 that define what Alice should do to run a local simulation algorithm. So what she does is something very simple. She prepares an EPR pair, then she runs the honest strategy, and she inserts 1 qubit of the EPR pair into the honest strategy instead of one part of the raw state, and then she measures the result. And then importantly, at the very end, she does something weird. That is, she decides what to do depending on this like if statement. The if statement that contains the post-measurement state that was created by measuring the honest strategy algorithm. Okay. And now let me just say that if this step was efficient, then everything else would be efficient, and that would break the assumption that it is hard to locally simulate. So we know that computing the if statement has to be hard. And if Alice, let's say, knew what the state psi xa is exactly, she could compute the if statement. So that's where some notion of not knowing the state that was prepared comes from. Okay, and there's a lot of details around that, but that's essentially the main message. Okay, and that's the last slide. So just a few open questions. So of course, it would be nice to have a complete characterization of the UCN assumption, which I think is a type of a physical assumption, right? Because on the one hand, we had learning with errors, and now on the other we have oblivious state preparation, but the gap is still pretty big. And I think it's also interesting to understand what's the right notion of of UCN, because I showed you two variants, but one can imagine very different settings. One can consider public, private coin protocols, independent questions, dependent questions, change the number of rounds. Should the verifier be quantum? Should it be classical? And I think some inspiration can come from physics, which of these models are correct, but also maybe some insights from TCS of like which of these models can in principle be satisfied, can give some potentially insights for physics. And okay, the last three maybe are not as interesting. Okay, good. So thank you very much. Yes.
Do you know if UCN gives you a proof of concept?
Uh,
Or some version of UCN?
So one needs to be careful because whether you start from the assumption that the verifier is classical or quantum.
Classical.
Yeah. So I'm not sure, but I haven't really thought about it, but it feels like the OSP is kind of a proof of quantumness, because if there's some notion of not being able to fully know what the state is, then it kind of has to be quantum, right? So maybe yes, but I would need to think about it. Yeah.
What was your result like for every results? Like for every entangled state, there's a game with this.
Should I go to a specific slide or no? What's
I think it was like earlier on you state you had two things on the right side that were like for every entangled state you have this computational non-locality. And I was just wondering if is it that you get like a particular game where you have this computational non-locality? Like it's like for every quantum.
Like this one. Okay. This one.
Yeah.
Yeah. So that's a specific game.
Okay.
So that goes through. There are some results that construct something called remote state preparation, which vibe-wise is similar to that oblivious state preparation, but with, let's say, with verification. And then we use another physics results that shows that if you were able to send quantum states instead of classical questions X and Y, then entanglement is equal to non-locality. And then instead of sending quantum states, we replace it with like a TCS tool to create the state with classical communication, but at the cost of computational assumptions.
So it's like
yeah, it's very specific. It takes like something known, let's say in TCS, and something known in physics, and puts it together by replacing quantum communication with computational assumptions, which is a very common thing, right?
I guess but the physics result gives you an efficient strategy for this. Like given the quantum communication, the strategy is in BQP.
Wait, which strategy is efficient?
You need, I guess, not only that there is a strategy with, there is a game with quantum communication for every unentangled state, but also that is an efficient.
Yeah, okay, yes, you're right. But it's very simple. It's like one quantum state on like, I think 1 qubit, and then you measure like very simple measurement on like 2 qubits. So there's no problems there. Yeah.
I had a question actually about is this notion of an entangled state? Do you need some kind of it needs to be like one of a poly entangled or something like that?
So that's a good point. But in essentially everywhere, the state that is shared is on like 2 or like max 5 qubits. So the complexity is not coming from the size of the quantum state, but from the size of the classical questions.
I see. Like the entanglement is like constant. And
yes, exactly. Yeah.
Is
Is this like a falsifiable assumption, like
That's I don't think so. It's like, how would you, in the physical world, how can you, because what would it mean to falsify? It would mean that for any two circuits, for Alice and Bob, you cannot find, different circuits that only share public randomness.
But because it implies that BQP is not equal to PP, and if you gave a BQP algorithm for a PP complete problem, that would
Okay. Right. Yes. Yeah.
Questions? Let's call it for today. We'll do the remaining talks at 3:30 tomorrow during the open discussion session.